In this video, I'm going to briefly discuss the basic concepts of graph theory that could be used in network analysis. Keep in mind that this by no means is comprehensive, and graph theory is by itself a fascinating topic to study. But discussion to that extent is out of the scope of this course, so what I'm doing here is merely to give some context to the network analysis within the graph theory field. We have often heard that a picture speaks 1,000 words, but a graph, in my opinion, speaks so much more than that. A visual representation of data in the form of graph theory helps us gain actionable insights and make better data-driven decisions based on them. But to truly understand what graphs are and why they are used, we first need to understand the concept of graph theory. Understanding these concepts makes us better programmers, but more importantly, for the context of this course, better data scientists. Put it concretely, graphs are mathematical structures used to study pairwise relationships between objects and entities, and it is a branch of discrete mathematics that has multiple application fields from chemistry, computer science, linguistics, operational research, and sociology. Uh, Here I can briefly give you a bit of history that how this field is even born. I don't know, probably you have heard of the Königsberg Bridge problem. This is the photo you are seeing in this slide. And this is a mathematical puzzle set in the old Prussian city of Königsberg, which is currently called Kaliningrad, I guess, in Russia, which actually led to the development of the field in mathematics that we today called graph theory. And the idea was basically there was this city, and the citizens of Königsberg would spend their days walking on these intricate arrangement of the bridges as you see on this river. Basically, it was several bridges, to be exact, 7 bridges that was located on the Prego River, and the main questions that they had, and they were trying to solve this question by just walking on the bridges without having any mathematical formulation to that, was that uh, is it possible that a citizen could take a walk through the town in such a way that each bridge would be crossed exactly once? So this problem has been on the table for ages, and eventually in 1735, the Swiss mathematician Leonhard Euler, which is one of the founding figures of many different mathematical disciplines, presented the solution to this problem and solved it once and for all, and concluded that this is not possible. And for doing that, he basically transformed the problem of the 7 bridges of Königsberg to the form of the graph that you're seeing on the left side. So these different islands were then the nodes, and the bridges were the edges, and then based on the degree of each node, he formulated a theorem and then concluded that no, it's not possible to do it. So this is where the graph theory was born. Of course, it has nothing to do with the network analysis we're doing now, but I find that an interesting and inspiring problem, in a sense that it was a real life problem, and then it was transferred to a mathematical formulation visualized by graph theory, and the answer actually became very easy. Now, if the knowledge was existing from the beginning, it wouldn't be such a problem in the first place. So enough of history, let's get back to our graph theory and network analysis. So we're talking about the network analysis here, and networks are really the graphs. You're seeing a sample network on the left side, and basically, put it simply, the main components of a network are the vertices and the edges. Of course, the edges could have weights, the vertices could have labels, and all those things. But basically, the main components of a network are the vertices and edges. And what do we call a vertex? It's also sometimes called a node. It's a set of objects that are connected together. Vertex attributes define a vertex based on its characteristics. For example, if we're talking about the network of the airlines, then our vertices are the cities, and the attribute associated to that could be the city population, for example. And edges, simply put, is basically this connecting link between every two single nodes, or between two single vertices. And if it is directed, what you're seeing here on the left side is an undirected network, an undirected graph, and basically it's basically intuitively easy to understand it. If there is no direction captured in the network, then it's an undirected graph. For example, between the node A and E here, we don't know if there is a direction for going from A to E, and it basically implies that the movement, if you're talking about, I don't know, a network of airlines, moving between two different nodes is possible. But if we had a direction, let's say from A to E, is more or less like a one-way road that you could only go from A to E, but you cannot come back from E to A. Okay, so this is basically the main components of a network. And we see the examples of network in our everyday lives. I already talked about the airline networks. The vertices are the airports, and as I said, we could have some attributes associated to the vertices, since the vertices are the airports here, so it could be footfall, terminals, number of staff, city population, whether it has international or domestic flights, freight, hangar capacity. And obviously the edges are basically the airplanes and the routes. And we could also have edge attributes. For example, when we have a thicker edge in this example, then we could say that there are more frequent flights between two different airports. The number of passengers that are being carried between two different cities is also could indicate the edge attribute. The plane type, the fuel usage, the distance covered. I mean, these are not always equal. Basically, you're drawing a graph no matter what length, how long you're drawing the line of the edge is not meaningful unless you capture it by associating a number indicating that this edge is longer than the other one. So these are all could be the edge attributes when we're talking about an airline network. But this is not the only network. We have banking networks, and then within a bank we could consider the account holders as the vertices. And then the information related to that, we have name, demographic, I don't know, different documents, the account status, balance, all these details. And edges indicates the transactions. If there is money transfer between two different customers all the time, and that could also indicate the attributes of the edges. One famous network that many of us are dealing with it there today is the social networks, and we as the users could be considered as the nodes within these social networks. And then what normally is collected could be our name, our demographic indicating what is our age and gender, who are our connections, who are we following, who are our followers, how many likes we have given to different points, I mean accumulatively, for example. Is there any community that we belong to? For example, in Facebook we already have these groups predefined, but in something like Twitter, you could do some analysis on the network and then realize that there are clusters here and there, probably not explicitly defined, but then when you see it in a network, there's a cluster of people somewhere, you could consider them as a circle. And then how they are interacting with each other, if they are retweeting each other's posts, for example, or liking each other's posts, then we would say that there is an interaction. And then also we could attribute some stuff like time and duration that they have been in contact with each other, what type of content they have, what type of topics they are posting most oftenly. And then physician network, it is something that many of us don't necessarily have access to it, but we are part of the information basically that is being communicated over the network. So the doctors are in this network, and then they simply could transfer the information of their patients between each other, and then it kind of improves the diagnosis of the patient, because they have access to more data. And supply chain network is something that has been around for ages, and it has been the discussion of many scientific problems, even like optimization problem. And in this example, we could consider the warehouses, for example, as the nodes or vertices. And then we want to know where they are located, what is their capacity, how much they could hold in them, what type of storage it is, and then the edges could be the trucks that are moving between these different warehouses basically. And then we want to know how much each truck can basically take from one node to the other. So you see, these are all our day-to-day examples that we see. And these are type of the networks that we are facing. But when we look at these, the question that arises is that having these networks, what sort of analysis we can do in them? So let's go through a few examples and see what are the common ways of network analysis. Marketing analytics is one of these type of common analysis, and you have faced them in your day-to-day life. Graphs can be used to figure out the most influential people in a social network. Advertisers and marketers can estimate the biggest bang for the marketing bucks by routing their message through the most influential people in a social network. And these people, I'm sure you have heard, are getting paid a lot just to put one single post, thousands of euros, because they have such a large outreach, and the network indicates that, the network analysis indicates that by posting one single thing, they can bring in a lot of customers. Backing to the banking network that we already showed in the previous slide. Banking transactions is another type of analytics. For example, graphs can be used to find unusual patterns, helping in mitigation fraudulent transactions. Or the thing that is very important and valuable these days is basically identifying the terrorist activities by analyzing the flow of money across interconnected banking networks. So as you already see, this network analysis could become very valuable in protecting ourselves even. We could also discuss about supply chain. As I said already before, this is one of the oldest mathematical problem existing, that graphs can help identifying optimum routes for delivery of trucks and identifying the locations for the warehouses and delivery centers and all these things. Going back to the applications that is useful in our life, pharma and pharmaceutical companies could actually use the network analysis as well. For example, they can optimize the route of the salesman using graph theory for cutting the cost, reducing the travel time for salesmen, but also network analysis is a very good tool for identifying the right type of medicine to be used on the patient. This is one of the approaches that we do in personalized medicine. For example, we draw the protein interaction in one individual patient, and mind you, it is different from me to you to someone else. It's quite personalized. And what this network tells me is that if I have a medicine that is acting on this single protein, but I am interested to affect another protein somewhere else, for example, to cure the cancer, what is the best node, which is the protein to take? Then choosing that best node indicates the best medicine. So that is why we are going toward personalized medicine, and in future, the the prescription for me is different from the prescription for you for the same sickness. So network analysis is pretty handy in there. And I'm sure you know the other about that. I mean, probably this is one of the first networks that come into mind, the telecom networks. And telecom companies typically use graphs to understand the quantity and the location of cell towers to ensure maximum coverage. So far we have seen of different use cases that networks are important and could be uh, utilized. The question that probably you have in mind is that why we need to use graphs, why we don't use any other sorts of analysis, which we actually do, but why graphs are so important. First of all, graphs provide a better way of dealing with abstract concepts like relationships and interactions. They also offer an intuitively visual way of thinking about these concepts, and graphs at the same time form a natural basis for analyzing relationships in a social context. So it is very versatile, and it's a good way to handle quite complex concepts. It is kind of abstracting away from too many details and having a whole picture in front of you. Another reason is that, like it or not, graph databases have become common computational tools and alternatives to SQL or NoSQL databases. So this is another reason that we need to study graphs. Graphs also used to model analytics workflows in the form of directed acyclic graphs. As I said in one of the first slides, we could have direction that some paths are forbidden and we cannot take, and this is basically how you define a workflow. Graphs also could be used as a form of neural network frameworks to model various operations in different layers. And neural networks is something that we are going to see later in this course. They are becoming one of the very useful and very common ways of using machine learning and artificial intelligence. Another fact is graph theory concepts are used to study and model social networks, fraud patterns, power consumption patterns, all these things. And social network analysis probably is the best known application of graph theory for data science. For example, Twitter analysis, I go back to that. You can get the data of the influencers and then how people are connected. You could probably, even based on the post and many different things, get an understanding on how they feel. They have sentiment analysis using social network analysis. So all these things are associated with the studying the graph. It's also used in clustering algorithms, especially k-means. I have already given an example about this at the beginning. When you see a graph, you could visually identify some clusters, and then you could go deeper in those clusters and see what are the common features that these group of people, if we are discussing a network that includes people, are clustered together. What is it that what are the similarities they have with each other, but at the same time, what are the differences they have with the other groups of people that are not in that specific cluster but are in the other clusters. This could give a lot of useful insight. It's giving insights in politics, in education, in social welfare, in so many different things that even if this was the only thing that you could get out of the graphs, it was a useful outcome of doing the network analysis. We could also use graph theory concepts to study the system dynamics, especially loops. If you start somewhere and we go through different nodes, and by the help of different edges, there's a possibility of getting back to where we were. So if you are interested in studying loops, that is also something quite important. Path optimization, as I said, it's one of the oldest concepts in mathematics that has been studying, is a subset of the optimization problems that also uses graph concepts, and there are several different algorithms. I gave you the example of Königsberg problem at the beginning, that we were asking whether solving a question is possible or not. And the fact is that in real life, solving many problems related to the graphs. I mean, if you what I mean is basically when you formulate a problem in terms of graphs or network and you want to find the optimal solution, normally it is so computational, and it happens in many cases, it is so computationally expensive that you really cannot go for the best answer. You are going for the optimal answer, which is good enough, but it's not the best one. And there is where we have path optimization or optimization in general coming into play a role. And also, from a computer science perspective, graphs offer computational efficiency. The big O complexity for some algorithms is better for data arranged in the form of the graphs rather than, for example, putting them in a tabular data form. So all these things that I said are some applications of the network analysis and graph theory, and this is important why we need to know about the graphs and the functionalities that they are offering. So let's go through a few graph theory concepts that are used in network analysis. As I said at the beginning of this video, it is not comprehensive. This is not all things you could do with the graphs, but this is not a graph theory course. These are the few things that you could use when you are doing network analysis. These are the few things you could use when you are using Python packages doing network analysis, but even there, you could do much more than this. It's just for you to get a beginning for the subject. So one of the things that we could study and analyze in the networks is the average of the shortest path lengths for all possible node pairs. This gives a measure of tightness of a graph and can be used to understand how quickly or easily something flows in this network. So probably this is one of the first things that one could analyze. It could indicate the amount of resources, for example, that you need to allocate for doing some sort of, I don't know, for example, marketing. One of the most widely used and important conceptual tools for analyzing networks is centrality measure. And centrality aims to find the most important nodes in a network. And already by saying that, you could think about the marketings. You could think about the elections, who to contact if you want to influence more people in that network. There may be different notions of importance, and hence there are many centrality measures. Centrality measures have a form of classification or types of centrality measures, and here I am going to list 3 of them. We have degree of centrality. It is probably the first and conceptually the simplest centrality definition. This is the number of edges connected to a node. In the case of directed graph, we can have 2-degree centrality measures, one for inflow and one for outflow. Basically, what I mean by that, if we have an undirected graph, the more the number of edges going out of a node, basically the higher the number of centrality. If we go back to the example of influencers, the higher the number of centrality measure, the more influential that person is. But if we have a directed graph, basically for each node we have some edges coming into the node and some edges going out of the node, and that is where we have 2 different inflow and outflow centrality. And if the number of outflow centrality is higher, basically that node has more influence on the other nodes. But if the number of inflow centrality is high, meaning that there are so many different nodes, people, whatever, that have effect on that single node. We could also discuss about the closeness centrality, and closeness centrality of a node is the average length of the shortest path from the node to all other nodes. And it is actually kind of important. I don't know if you have heard about this story, that when you tell somebody the news, the further the news gets, the more twisted the news will become. So it is safer and more valid the news you get from a closer connection than when it has gone through, I don't know, 10 different people until it got to you. The closeness centrality shows basically how quickly that news, that information is going to spread to the nodes that we are interested in. And we have betweenness centrality, and this is number of the times a node is present in the shortest path between two other nodes. And these centrality measures have variance and a definition that can be implemented using various algorithms. And you could use them when you are doing network analysis with the help of Python, especially that in this course we are discussing the Python and its packages. We also have network density, and it is a measure of how many edges of a graph a graph has. The actual definition will vary depending on type of the graph and the context in which the question is asked. For example, a complete undirected graph has a density of 1, while it is 0 for an empty graph, and graph density can be greater than 1 in some situations if we have loops involved in the graph. So this was a short, quick introduction into the network analysis as a sort of theoretical base. You got an understanding what are the underlying ground for the network analysis, which is the graph theory. You got to get familiar with a small number of graph theory concepts. We had a bit of history, and more importantly, we realized why network analysis is important, why graph theory is needed to be studied, what are some common use cases that network analysis could be applied to. And as I said in one of previous lectures, the main goal of this course is basically tell you where to look for knowledge when you have a problem in hand. What I mentioned here are by no means all possible use cases or application fields for network analysis, but this gives you an understanding that on what sort of topics you could go to the knowledge of network analysis that you have and dig a bit deeper, probably, to learn more and use network analysis when you find it a suitable case study. And for that, when we get to the practical part, what I suggest to use is the NetworkX Python package, which is a very good tool for analyzing the networks, and it provides simple, user-friendly functions to produce some of these, all of these basically, network aspects that I mentioned in this video. And we're going to play our hand a bit in the next video that I'm going to put for today's lecture. But for now, bye and see you in the next video.